Hello, I hope you've been looking after your bodies as well as your coding skills. In this video, I'm going to be sharing how I created um, this scene. It's a 2D scene rendered in Three.js. It uses a custom post-processing effect, which is done using a off-screen render target, and then it's passing that render target texture into our custom shader so that we can write any sort of code to apply changes to the final output. As you can see here, we've got a vignette, we've got noise, and then we've also got a kind of distorted, blurry layer which becomes more dominant as the content reaches nearer the end of the outside of the vignette. So you could look at kind of composing the vignette and the noise separately, but to create something as kind of bespoke as this ghost-like waviness, you really need to write your own fragment shader. And in this, I've just put all of the code for these three effects into one effect shader. Hope you enjoy, and if you get any value from this, please give me a thumbs up. The code will be available in the public repo with the link in description, and let's get going. Been using React 3 Fiber for any amount of time. You may have come across the post-processing effects, and so there is actually a dependency of a package in which you can easily add effects to your React 3 scene. And it works like this. You essentially import the effect composer, and then you can choose from a selection of kind of pre-built effects. And this optimizes the application of these. Each of these will be its own shader and this will kind of chain them together in a performant way. So for a lot of use cases, simply exploring the effects that are on offer here is a good starting place. So we've got noise, pixelation, bloom, sepia. There's a ton of them here. If you want to write custom effects, you can do so by extending the effect class and passing in a fragment shader. So if, for example, you wanted to use the bloom, but you also wanted to apply, and they've even got a grid, but I was going to say if you wanted to write a grid, or so you want some sort of color distortion that can't easily be achieved through these preset effects, then you could look at creating a custom effect and implementing it inside of the effect composer like this. Whilst I was looking into kind of how this works, I wanted to see if I could essentially build this from scratch, or kind of using the lower level components and processes. So yeah, let's take a look at the code. I've recorded two earlier videos, one on the image sequence, which is on the kind of header section on this example site. So this image sequence was rendered by my friend and amazing 3D artist Derek. We have put it into a transparent canvas and overlaid it on top of the text. And I've got another video showing how that works. This is dependency free, although, well, it actually uses GSAP to control the scroll, but it's not using Three.js. And in the other video recently, I worked on the background shader, which is what you'll see here. So this video is kind of a follow-up in this series. And if you haven't checked out the background shader video and you're new to fragment shaders, I'd recommend kind of starting there. Okay, so we're in the code now, and the process will be loosely as listed here. We've already looked into the existing effects composition for pre-built effects. Then we'll set up the canvas, create the background shader. I won't spend much time on this because there's another video more dedicated to that, as well as kind of introduction to fragment shaders. And then we'll update our image sequence so that it's rendered inside Three.js, and then finally we'll set up the post-processing effects. The canvas is imported from React 3, Fiber. These are some recommended settings for post-processing. I've got a 2D camera, orthographic camera, because this is a flat scene. However, this could be changed, and I plan to do a video in the future where we've actually got a 3D scene with post-processing. And then I've got a main component. And the main component is where our two planes are. So we've got a plane for the background and a plane for the image sequence, which is the bottles over the top. If I go back to the browser, this can be found in the FBO effects page. Okay. So yeah, we've got the background plane with the texture moving slightly on the x-axis, and then we've got the image sequence here. So the background, we'll start with that first, is really just an image texture that's passed through into the background shader, and the background shader then receives the texture color, it samples the texture color, applies a color conversion to make the image look as it should, and then it returns that color. We're also adjusting for aspect ratio and moving it slightly on the x-axis with the time. So if I change this value, then we get a much quicker movement. So I played around a little bit fiddling with that. If I take the aspect ratio off, it's bigger. In fact, that actually looks like it's more correct. Let me just check the, oh no, see, they are quite small, tightly coupled tiles, so this is correct. So yeah, we're adjusting the UV for the aspect ratio and then pushing it along on the X using our uniform time value. And then we're tiling it with the fract glsl function. Like I say, check out the other video that I've done if you want to kind of just learn more about that. Then the image sequence, so in the version in which I was loading the images into a HTML canvas, the process was slightly different, but essentially we're still generating an array of image sources using an index, and these are all in this folder here, public folder. And then with these image sequences, we're using the use texture hook from React 3 Dre to load all of them into this array of textures. Once the textures have loaded, we're then going to assign our local ref, which is the current texture, the first image. So that will happen immediately. And then we're creating a GSAP scroll trigger, which will track the scroll from the start at 0 to the end of the screen, at the end of the page, which is currently just a 200 view height main element. So adjusting this will affect how long that scroll takes. And obviously if you were having other sections in here, it would probably just be tracking the scroll of the relevant section. So back to here. When it updates, same method as outside of Three.js, we're just grabbing the current texture index from the progress. So the progress between 0 and 1, multiplying it by the number of image sources. So this could be images like that. And then we're assigning the current texture to that texture in the array. Now we've got the texture that should be shown. We've set up our image sequence shader to receive a texture and a texture aspect, and also the actual viewport aspect. Again, I covered this in another video, but basically we're just defining the uniforms, creating the shader with the Vertex and Fragment shaders, creating a shader material. So in the use frame, we are updating the image sequence shader's current texture, and we're also passing time into the background shader in order to move it along. So now what we have is our image sequence responding to scroll and our background plane moving based on the time input. So this is our basic scene. Obviously, you could have 3D objects in here, you could have more layers, whatever. This is just quite a basic kind of minimal setup. So moving on to the effects then, I've created a custom effects component down here, and this component receives children, and those children are going to be the main scene that we just looked at up here, so our foreground, background. So yeah, the custom effects is going to wrap the other Three.js components, React 3 fiber components, and inside of it we take the children and we then create a portal which is off screen with the FBO scene. So the FBO scene is just a regular Three.js scene, and so this will basically be off screen, and the visitor, the user, won't see this. So if I update the main canvas to include that wrapper now, so now we don't see anything. We have a render target, and so the useFBO hook is a frame buffer object. What that will allow us to do is inside our useFrame hook, we can get the GL from the renderer from the frame hook. We can set the render target to this local custom one. We can then render the FBO scene, which is the one over here, and then we can set the render target to null, get the texture from the render target. So essentially it will have rendered a frame for the scene that we just set up, and then it's going to pass that texture into our custom material. So our custom material is another shader material, and it receives the scene texture. So it's kind of like taking a picture of the entire Three.js scene and passing it into this shader so that we can then distort it or apply effects to it as a single image, as opposed to trying to do it to different kind of layers individually. So this is the process for full screen post-processing effects. We have the shader, and that shader will receive our texture and then do something with it. It will then render the regular scene so that our component here, this ScreenQuad with our shader, gets displayed. The recommendation is to use a ScreenQuad over a plane because it is simpler for the GPU to work with. It's like a single triangle as opposed to two that would form a plane. And there are articles on the benefits of doing this, but the custom effects, this effects composer is using that under the hood, so it makes sense to do that here as well. So we have our ScreenQuad full screen and our effects shader, and that effects shader is going to receive the texture of our main scene after it's been rendered into our render target. So quite a lot going on, and I hope you're with me, but if not, just do a bit of research on the render target and the kind of off-screen scene. So in the effects Vertex shader, we actually need to have made some changes to this for it to work with the ScreenQuad. At first I was a bit confused as to what needed doing, so I did consult my always on coding buddy and found that it uses these normalized device coordinates. So the Vertex shader doesn't need to do so many calculations. This is the regular Three.js one, which I passed to it, and then one of these solutions worked, but basically it's a lot simpler. And that's all we need to do. We just need to have a simpler Vertex shader in here. The fragment shader will then still receive the varying UV and can act normally with that. Let me show you how this is looking now. So there are a few different things going on here. We've got an obvious vignette, which is sort of a really dark grey coming into the middle. We've also got noise, and when the image sequence, or when any of the scene texture kind of reaches near the edge, it's being blurred and warped like this. So this is a very kind of custom effect that you really would need to code yourself. I know that there's a noise and there's a vignette effect shaders, but they don't have this kind of use of the vignette to distort the image and blur it. So I'm going to talk through that now. I'm using glsl to import a noise and a blur function. So these are both npm packages which are installed, and in order to get those to work, we'll need to make sure we've got raw loader, glsify loader, glsify, glsl noise, and the fast blur installed. Those packages are then configured in Next.js so that during the build process it will apply the transformations, or it will import those dependencies inside our fragment shader. This is equivalent of getting that code and pasting it at the top here. It just is a bit easier to work with. So yeah, the effects fragment shader receives time, resolution, and the texture of the scene from the JavaScript, and then it receives the coordinates from the Vertex shader. So we're going to start by just commenting out this and then simply returning the scene color. So what we can expect to see now is no changes. It just looks exactly as it does, which is what we want. It means that the setup is correct. Now, if we wanted to add a vignette, what we're doing here is we're calculating the distance of the current coordinate to the center. And then we can adjust how it looks using a smooth step. These values can be tweaked with to change the kind of intensity of it. And now if I mix that vignette with our scene color, so we're going to mix that and we'll return that. So now we've got our custom vignette here. We can change the color quite easily. And so this applies over the entire scene texture image. Now, if we wanted to add some noise, we can use our imported noise function, pass it the required vector 3, which is multiplying the UV by a large number. If I don't do that, we'll see how that looks. And then, so we've got our X and Y times 2, and then we've got time so that it moves. If we take out time, we've got noise, got a value for the noise at this coordinate. We've got a color for the noise, which is just a grayscale color between 0 and 1. Yeah, I should mention this is normalizing the noise because noise is between -1 and +1. So by doing this, we are moving it to between the range of 0 and 1. And then we're creating a color. So obviously the color value is between 0 and 1 with full opacity. So now if I blend that in, what we'll see, we've got our scene with our vignette, then we've got our scene vignette, and then our noise over the top. So you can't really see the noise there, although you can. I think it's just really big. And so this is why we multiply the UV value. So the higher that number, the more noise there is. So hopefully you can pick that up on your screen. And then if we want to have movement, and put in time, but we need to multiply time so that it's kind of giving that fuzzy effect. If I just reduce this down here, that should be more obvious what's happening. So that noise is just overlaid over the entire final color with a bias towards the final color. If we put 0.5, we're going to be right there in the middle. So the kind of more complicated part of this was blurring the scene. And so in order to do that, there's kind of a couple of steps in which I took. I created a local UV initially assigned to the varying UV, generate some noise again with the UV multiplied but by a much lower amount, and the time is slowed down. And then this is then divided by 20 or times by 0.05 in order to reduce its effect, because what we're doing in the next line is adding the noise value to our UV, and then when we sample the well, actually we're blurring it using glsl, but if we don't blur it, let's not do that just yet. So if we do this, we're sampling our scene texture using our distorted UV value. So what we'll get here is a different, well, kind of like that waviness. So if I change this to show that, now the entire scene image is been distorted like that. This is pretty cool. It's kind of how you can create fisheye effects, stuff like that. Now, before we blur it, the actual mixing of these yeah, I've got American spelling here and then English, British here. I'm going to change this. Hopefully everything's working. Yeah. So we've got our blurred. This is actually our noisy scene here. And then we're going to use our vignette value to mix the two of them. So if I create a new value here, final color, we take in our original scene and then our blurred scene, and we mix it using the vignette. So now what we'll see is that vignette that was applied is the value which has been used to mix the kind of wavy version of it and the regular version. So towards the edges it's been distorted, and then as it comes in it's no longer. And I can do final color equals a mix of the final color and the vignette color, and now we can see that more clearly. So now as the bottles move, or whatever's in the scene, as it gets nearer the edge, it becomes a kind of distorted, wavy version of itself. If we play with the vignette values, we can see how changing those increases it a lot. So now it's barely visible, it's just happening over here a little bit. The blurring of the scene is using the glsl fast Gaussian blur. And so if we see here, there are a few different versions we can import, and it requires the image, the UV coordinate, resolution, and the direction of the blur. So if I delete this one, we're going to still use our noisy UV. The resolution has been passed in, and then we can adjust the blur level here. So now what we have is almost like a ghost-like version of that sort of overlay that becomes more dominant towards the edges, where the vignette value increases to 1. So yeah, it's pretty cool. That's basically how this effect shader has been composed. You could change this however you want once you have a bit of an understanding of how these work. There's loads of code samples online, or you can use ChatGPT to help change the code. Yeah, so that's that. I hope you learned something and this has given you a few ideas. As always, appreciate you being here and look forward to the next video. I'm going to be doing more stuff with Three.js, but also some more kind of React Next.js type content around maybe some translations like locales, just useful things. All right, cool. Look after yourselves. Peace.